It's my great pleasure to introduce our distinguished speaker today, Professor Alexandra Silva. Professor Silva is a renowned theoretical computer scientist whose research has significantly increased our understanding on semantics of programming languages and modular development of algorithms for computational models. Professor Silva is currently a professor at Cornell University, and previously she held professorship at University College London. She has received several prestigious awards, including Roger Needham Award, Pressburger Award, Leverhulme Prize in Engineering, and a Royal Society Fellowship. Today, Professor Silva will talk about outcome logic. Please join me in welcoming Professor Silva.
Okay, thank you so much. Can people at the back of the room hear me okay? Is okay? Cool. So yeah, thanks for this invitation. It's a pleasure to be here, and I'm really glad I made it despite the snow and the cold and the overflow at the hotel last night and all of that. I'm glad to see the room packed and lots of people here. So what I want to do today, I want to talk about this project I've been doing for a few years with my student Noam Zilberstein and some collaborators on outcome logic. And I want to tell you about sort of the latest results. And I'm going to use a lot of examples trying to bring some intuition for the problem we've been trying to solve. This sort of program is a little bit like a tale as old as time. They're sort of the beast, which are programs, and programs can get quite complex and can have different sort of constructs. And I'm in particular, for those who know me, you know that I'm particularly interested in probabilistic programming. So programs that have access to sampling and random variables and that can manipulate values based on that. And then on the side of the beauty, we sort of have formal methods. And for the purpose of this talk, I'm particularly interested in the beauty of logics. So how to use logics to sort of attack program analysis and program verification. And there's been a lot of work done on program logics, right? So what I'm going to tell you today is really not just my work, but it's sort of founded on a huge body of work. There's a paper that I did not reference later, but might be worth mentioning. There's a paper that Patrick wrote a couple of years at Popple with a huge cube of program logics that I will be touching upon at points, but I forgot to add a reference to that paper. But that cube and also another thing I wanted to mention is a slide that Ilya Sergey has on his website on concurrent logics. And I think that slide has probably about 20 or 30 logics in it. It sort of shows that there's a huge space of work. And each of that work has a purpose. As a class of programs, they're tackling a class of properties. They focus on different aspects of how you can use a program logic. But they all come from this sort of idea that analyzing programs you should be able to specify it in a simple and intuitive way. So you should be able to write down a certain program. I use C for programs here for command. And you should be able to somehow write down specs that look a bit like this. If P holds before the program executes, then at the end Q holds. And this is a very powerful way to reason about programs, because depending on how you set up P, you might end up pruning the space of your program, and that might help you reason about more complex properties that you might otherwise not be able to because C is too complex. Okay, and this is what sometimes is referred to as the axiomatic view of program semantics and program analysis. And so this is, for the purpose of my talk, when I say program analysis, program verification, this is sort of what I mean. I want to build logics that look like this for certain classes of programs. Okay, and these triples or program logics in general have formed the basis of many analysis and verification tools. Many of you have heard probably talks about infer, which is this tool that uses separation logic inside Meta. There's Jillian, which is a tool developed at Imperial. And then I sort of separated them in two groups. There's this group of tools here on this side, which are more sort of on the theorem prover or proof assistant space. So we have the large project on Iris, on concurrent separation logics, and then Daphne and Coq and Lean and Viper. So there's sort of a wide range of tools that have implemented different forms of program logic to do program analysis. Okay? But what I'm interested to tell you a little bit about is this class of programs that I call probabilistic concurrent programs. And I want to sort of show you that up to this work we've recently done, there was not really a good way to analyze these programs using this sort of intuitive program logic approach that we have done for sequential programs, concurrent programs, probabilistic programs, but for the mix of them, nothing much was there. And what are these programs? Why am I wanting to mix probabilities and concurrency? So here's an example that's going to be my running example for the whole talk. And then I will tell you where this example sort of comes from, and more broadly where these programs occur. But let's start with an example so that we sort of get some terminology in place. So I have a language that has two things that might not be standard. One is I can sample from a distribution, and here in pink I have this command flip, which is basically just allowing me to flip a coin or to sample from a Bernoulli distribution. And I can store the result of such coin flip inside the program state, inside the program variable. And the other thing I have in this language is this operator parallel that allows me to execute basically programs in parallel. Okay? Now, if I give you a program like this, you might wonder, what does it do? And what questions may I want to ask about this program? So here's one question. Is Z, variable Z, a good source of randomness? So let's see how we build variable Z. So we have a few variables. We have y, x1, and x2. And basically, y is set to 0, and then later copied to x1. And x2 is coming from this coin flip. So x2 is clearly a good source of randomness because it comes from a coin flip, assuming this flip is implemented in some sensible way. And then z is just the XOR of these two variables, x1 and x2. Remember, x1 is definitely 0, or is it? Steve, are you awake? Do you want to help me with this program? Is x2, is y definitely 0? Oh. Sorry. See, I was hoping Steve was going to help me with this example. Okay, I have...
You never said anything about the scheduler.
Okay, I never said anything about the scheduler. Someone is catching me on my explanation. So what can happen here is that indeed I have this parallel here as this y being set to 1. So if I don't tell you anything about the scheduler, when you get to z, you actually don't know if x1 is 0 or not, right? Because you start with y is 0, but at some point in the execution of the second program, you might have set y to 1, okay? So here's challenge number 1, right? When we have these concurrent programs, you have to worry about things like schedulers. But worse, I now have this probabilistic coin flips. And so I also have to worry about other things like correlations and how they interact. But let's focus on this particular program. What would it amount to say that Z is a good source of randomness? So if I would want to specify this in a program logic, in an imaginary program logic, which we don't have yet, this would look something like this, right? I mean, intuitively, I would want to say, without any assumptions, I would like to run C and be able to assert that variable Z is distributed according to a Bernoulli distribution of bias a half. So it's a fair coin flip, okay? So this is what I sort of would like to do. And so during this talk, what I want to sort of show you is what are the challenges and what are the sort of hurdles in designing a program logic to derive a triple like this for a program that has both coin flips and parallel. Ilya.
You didn't say anything about the memory model. I assume the program on the previous slide doesn't have an undefined behavior.
Indeed, I haven't. That's another challenge that actually I'm not even going to touch upon my talk. But yes, there's also the issue of memory model. Indeed. Okay. So I promised you I would say at least a few words about why we care about these programs. Like, why are we just making up something, which we sometimes, I'm a theoretician, as Ashutosh said, and sometimes we do that. We create our own problems. We have probabilistic programs. We have concurrent programs. We put them together. Why not? But actually, these programs are interesting because they can be used to formalize correctness of certain randomized distributed algorithms. For people who are familiar with some of these this literature with a long tradition, for instance, the dining philosophers. Okay, that's an example of a randomized distributed algorithm for which, so far, we don't have a formalized proof of its correctness. Okay, and this would be really interesting because a lot of the papers on the randomized distributed algorithms have, of course, analysis of the algorithms that is more pen and paper and based on sort of expectation-based reasoning on why the algorithms are correct. So it would be really cool if we could formalize them in a language and have a program logic that you can mechanize and actually prove them correct or find bugs. I mean, these programs are quite subtle. These algorithms are quite subtle, and it would be interesting to sort of do that analysis. And then, less long tradition, but currently very hot. These probabilistic programs appear in a lot of AI and ML applications. And these days, with LLM architectures and whatnot, the use of parallel is also becoming really common. So that's another source of examples that one could find to formalize in this language. These programs are a good target for formal methods. As I just mentioned, program behavior is very subtle, and Ilya and Shira mentioned two things. Both the memory model and the scheduler are hard to reason about, and once you add these coin flips, then you have to worry about correlations between your variables and how these correlations actually interact with execution. And if you really want to be sure that your program does what it's supposed to be doing, then having some form of automated reasoning is essential. And just to sort of finish the trifecta, they are also a good target for program logics because the complexity of these algorithms, these randomized distributed algorithms, really demands that you have methods that are scalable. And program logics, one of the biggest sort of strengths is that they offer you this compositional reasoning. So this is sort of a good playground for program logics. Now let's go back to this running program. So this running program is, we call this an entropy creator because it's sort of creating this variable z. And why is it challenging to execute this program? I already hinted at some of the things here, but just to recap, if I write this program in a certain language, and I want to provide the language with some form of the notational or operational semantics, the first thing I need to understand is that a construct like x2 is assigned flip a half, asks that my semantics needs to be able to handle some form of probability distributions. And here I should say, for the people in the audience who are familiar with probabilistic programming, that in this language, I will eventually want to have loops. So even if I only allow Bernoulli distributions, I can then build all kinds of things from coin flips and while loops. So having just flip is not actually so simple as it might look at this point. Okay, so we have flip, and we need some sort of probability distribution in the semantics. Then we have this parallel, which because of the scheduler, or how we choose to encode the scheduler, will break compositionality of the semantics. Why is that? So as we put more threads in parallel, so let's imagine I start with the program here on the left of the parallel, right? And I give it some semantics. That semantics has to somehow take into account the fact that in an open world, if I put the other program in parallel, it's actually going to affect my semantics. So we have to be a little careful about capturing all these possible sort of interleavings that happen from scheduling other things in parallel. And this is what makes the semantics really sort of very interesting mathematically and very challenging. And then the last thing is that this is a very brittle programming language, or giving semantics to such programming language is very brittle, because minor changes to a program might really break your intuition on what's happening. So let me show you this by example. So I showed you this program before, and I sort of argued that, you know, I have my x2, which is sort of a high quality randomness. I have this assignment to x1, which is low quality because y is just a deterministic value. But, you know, I will show you at the very end of this talk that this value z is actually distributed according to a Bernoulli distribution. So it's a high quality randomness source. And so I will show you at the very end of my talk that this triple is valid for this program. But here's what happens if, for instance, we shift those first two things. So you see what I did here? So let me just go back for a second. So in the first program, the program I'm using as a running example, I first store y in x1, then I flip the coin, and then I calculate z. Now, in the second program, I first flip the coin, and then I assign variable y to x1. And so, same question, is z a good source of randomness? I mean, if you just squint at it, you might think, sure. I mean, nothing really has changed, has it? Yes, some people say yes. Who wants to okay.
The scheduler can, if the scheduler can see x2, then something has changed.
Okay, so the answer here in the front, if people didn't hear in the back, is that if the scheduler can see x2, then something has changed. So let's make this a little more concrete. So indeed, this will be a low-quality variable, randomness variable, and this triple will not be valid. And why is that? So if we write down the execution of this new program, here's what it looks like. I assign 0 to y, I flip my coin, and then based on whether x1, you know, whether my coin flip, whether my x2 is 1 or 0, I can do different things to the parallel thread. So indeed, as Shriram was saying, the scheduler can now force z to be 0. So think of this almost like an adversary, right? The scheduler is an adversary, and it's like playing against you. And if it has the information about the coin flip, then your XOR can be fully determined by what the scheduler does to that second thread. Okay? So I hope this example sort of gave you a glimpse of what is at play here. So we have these programs that can manipulate random variables and have these parallel threads that we need to care about. So we need to have some form of scheduler or some form of parallel execution. And we would like to reason about them using program logics. So here's what we would like. We would like to have this language have a compositional semantics. We would like to have some proof rules that are somewhat intuitive and that can handle this mix of effects, because you can think of probabilities and parallelism as a sort of an effect in the sense of a monad. And here, for those familiar with this old work of Varaka and others, handling a mix of effects when you have probabilities and nondeterminism or probabilities and concurrency can very easily break the compositional semantics. So wanting these two things requires a little bit of care. And then the other thing we would like to have unbounded loops in the sort of programming language, and then later on also to have proof rules to reason about unbounded loops. Okay. Now, we've done some progress towards this, and I want to tell you a little bit about that. The first thing we did, and that's appearing at Popple on Thursday, we've sort of like ticked all these boxes, but for a restricted language. Namely, we replaced parallel just by a non-deterministic choice. So you can think of a a non-deterministic choice as sort of a demonic semantics in the sense of an adversary, if you think that your adversary is playing against you. And so what did we do? We designed this language that looked exactly like the one I showed you in that program, but without the parallel, with a sort of non-deterministic choice. And we did a program semantics based on what we call, or what is called, convex power set. So let me spend a few words on this. The scheduler, so all the work we've been doing on this uses the notational semantics. And the reason why we went that way is that we want to sort of talk about the whole distribution that the program is manipulating, and not just sort of stepwise distributions. In order to do the notational semantics in a language where you have any form of non-determinism or parallel, you need to be able, your semantics need to be able to encode all these behaviors that may occur. They may not occur if the scheduler does not do it, but it could occur. And so your semantics needs to capture all possible executions that your program might see depending on the variables that you are manipulating. And so this convex power set disappears in sort of old work of Annabelle McIver and Carol Morgan, and someone else that I now blanked out. I apologize for, okay. Sorry, I blanked out the third name, so I apologize. But so the convex power set appears in this work back in the late 80s as a way to capture in a probabilistic language with a non-deterministic choice, which was somewhat restricted in their work, to capture all possible schedulers. So if you write a property, and so Annabelle and Carol have along the years worked a lot on expectation-based reasoning. So all their work is sort of targeted towards expectation-based reasoning. And what they wanted to capture there was basically this idea that for any scheduler you might choose, I can still prove this lower bound in my program. And so there they introduced this idea of using a convex power set to capture the semantics. And what we did in our work, we took that idea and we ran with it and proved that you can actually do unbounded loops. So you can basically compute fixed points. And again, I should give credit that a lot of these covering unbounded loops uses some old work on domain theory and work that goes back to Claire Jones and other students of Gordon Plotkin. There's a real rich line of work there that is finding, I think now, a lot of applications in this world of program logics. And so we sort of took bits and pieces of different works and put it together towards this language. And then we went on and designed a program logic that has rules for loops based on certain termination conditions. And there, thing you might have seen here on almost sure termination and so on plays a role to make sure that you can have sound reasoning around loops. And so details on this will appear on Thursday at Popol just after lunch. I encourage you to attend my students' talk then. It should be fun. Okay, and then from here, we wanted to basically drop the restricted bit. We wanted to go and do something that had concurrent work. And as it turns out, this was harder. Oh, sorry, I should have said. This is joint work with my student, Noam, but also with Joe Tassarotti and Dexter Cousin that appears at Popol. And so then we wanted to go and do something more general and do probabilistic concurrent outcome logic. And this is, again, joint work with Joe and my student Noam. And as it turns out, it took us a while to realize this, but just removing the restriction on just having non-determinism versus parallel, the convex power set was not enough. I mean, originally we thought that the convex power set would give us all we needed. And then slowly we realized that was not the case. And so we developed a new structure to give program semantics. And this I will give you details of in a moment. And we derived some rules. But as we did this new structure turned out to not exist in the literature. And so a lot of these domain questions about solving fixed point equations were not there. So we couldn't just take some old work and have unbounded loops. So in this work on probabilistic concurrent outcome logic, the language is the full language. It has a compositional semantics, but we only have bounded loops. So think like a for loop. That's the only thing we have. And so we thought a little more about it, and we now developed the domain theory for this new structure, which again, I will give you details in a second. So we did a whole paper on the domain theory of this new language, but we haven't gotten around doing the proof rules. So hopefully soon, I can tell you the full story. But today I can't, because we don't have. So we've only made it to the point where we have a full semantics on one side, we have a nice proof rules on the other side, but we don't have both together. So what I will do today, I will mostly show you examples from this draft, where we have these proof rules, but no unbounded loops. So the example I showed you was not using loops anyway, so I can show you the proof in that setting. So what I will do now for the rest of my talk, I will show you a little bit about this new structure to give the notational semantics to programs with concurrency and probabilities. I want to really spend about 10 minutes or so talking about the works we sort of got inspired in, and there's works also appearing at Popple this week that touch upon some of the things we've done. So I want to spend some time doing that and then show you some of the technical details of this new structure. So let me sort of talk a little bit about these many threads we were trying to bring together. So there's a lot of work on concurrent separation logic. I put Iris here, but really there's much more. From the very beginning, when CSL was invented, to all the many variants that have appeared in the literature, as I mentioned in my second slide, both Iris and Jillian and all kinds of other tools implement procedures for separation logic, for concurrent versions of separation logic. There's like a whole list of things. Probably this week at Popple, there are papers that touch upon these sort of CSL-like languages. In the last 5 years or so, there's also been a lot of work on probabilistic separation logics, starting with PSL back at Popple 2020, and more recently with Lilac, which is a beautiful framework that appeared at PLDI in 2023, and Bluebell, which I believe is appearing at Popple later this week. There's a lot of efforts in sort of reasoning about programs that manipulate random variables. And some of what I will show you here was particularly inspired by these three works, PSL, Bluebell, and Lilac, and the way they reason about independence of variables and conditional independence. And I really, again, one more plug for the Popple program. If you're here for the rest of the week, do attend the Bluebell talks. There's a lot of insights there on designing a language. Now, what we want to do is bring these two things together. And in order to bring these two things together, concurrent and probabilistic, we need to draw lessons from both, but we also need to be a little careful about how these things get combined, because easily you can break, for instance, compositionality of the semantics. So let me tell you about some things from this space that we drew on and that really played a role in the design of the language. So first thing is, from going back to the original design of CSL, here's one rule that is really crucial in concurrent separation logic. What does this rule say? It says, if I have two programs executing in parallel, I can independently analyze them, and then I can say something about the overall composition as long as I have separation. Okay? So this basically tells me if my programs, for instance, are executing in different parts of the memory and they don't interact, then I can do compositional analysis. Okay? So this is one point. Now, if C1 and C2 are not just regular imperative programs but have probabilities, what does this mean? Okay? And this now goes to PSL, where the sort of key insight behind PSL is that separation can be interpreted as probabilistic independence. And sort of the beauty of PSL is that they drew up a model, which is really a model in the sense of the same model as in separation logic, is what is called a model of bunched implications, where they interpreted the separation as probabilistic independence. So for instance, here's an example. If I do 2 coin flips, x and y, so I do 2 coin flips and I store them in 2 variables, x and y, and here in the precondition, you see the star from separation logic, and what this is saying is basically just saying x is pointing to some memory, y is pointing to some memory, and they are separate, so it's not the same memory location. So if I have that in my precondition, then I can basically deduce that x and y are probabilistic, so are random variables distributed according to a Bernoulli distribution, and they are independent in the sense of probabilistic independence. Okay? And what is sort of neat about this probabilistic parallel rule is that it literally looks like the same as the CSL rule. It's just that the interpretation of this separation is now different. Okay? So that's one insight from PSL. Now going back to CSL. CSL has this rule where it says, okay, if you have shared state, because in that first example of CSL, I was talking about separating the state, but if you have shared state, you can still reason about parallel threads, but you now need to bring into play an invariant. Okay, so if you bring invariants into play, then you can still apply almost the same rule. So for instance, a program like this, where I assign 1 to z and then I execute these sampling instructions in parallel, I can still analyze because I can add an invariant to the rule that says z is in 0, 1. Or, you can even go further and say that z is in 1. Why not? But you can sort of like specify the value of z deterministically. Okay? And so, again, you can reason about shared state as long as you have invariants. Now, the problem with this is that, in this example here, z is 1 is a deterministic action. And if suddenly I allow randomized shared state, which in this new language in which I want to have coin flips and parallel sort of live together might happen, then we have a problem. So here's another example, sort of flipped in its head from the previous one, in which I flip the coin first, and then I do something with x and y in parallel. What can I say about x and y now? I mean, they're clearly not independent, sadly. But there's something here that I might still be able to say. Can anyone guess what I can say about x and y? Yes? Exactly. So they are not independent, but they are conditional independent on z. Okay? So in a world in which I have some form of shared state, and that shared state is randomized, I need to be able also to capture and reason about conditional independence. And this is something that, the work on Bluebell and Lilac and other works have beautifully captured on how you do it. And so what we did in our work is to observe that in order to reason about conditional independence and deal with parallel, you need to sort of break down the outcomes of the sampling operation. Okay, let's think for a second intuitively what this means. So when I say x and y are conditionally independent on z, it basically tells me I need to know z first in order to say something then about x and y, right? So intuitively, if I give you a list of finite values z can take, then you can prove one by one that x and y are independent. Now, of course, in a real probabilistic world, you don't have a finite number of values, but let's for a second imagine you do. That is what it boils down to. Once I give you the list of Z, you can prove probabilistic independence. And so what our work sort of exploits is exactly that idea, is that conditioning boils down to breaking down the outcomes of the sampling operation. And so what we've done in our work is every time we can prove something about Z of the kind Z becomes a Bernoulli a half, then that expands to this thing here. That looks funny, and I will explain in a second what it means, but intuitively it just says my Z, my variable Z, and so note that there's a capital Z and a non-capital Z. So the capital Z is a meta variable, and the little z is the real program variable. And what this is saying, this is a program logic construct that says, create a meta variable that is distributed according to Bernoulli a half, but you could put anything there, and assign it to Z, and take a big outcome conjunction. So you can think of that big O plus as sort of a conjunction of all possible values I can give this meta variable. And with this in mind, that's how we can expand, that's how we design the logic. And so the key ingredients in our logic are basically separation, in the sense of separation logic, but now interpreted in this probabilistic world of independence, and the fact that we have this outcome conjunction. And this outcome conjunction allows you to talk about how to break down a distribution in smaller pieces. Okay? And then, of course, the devil is in the details and the semantics, which I will tell you in a little bit more details about. But really, if you take something from my talk, is this slide, is that you can marry separation in a probabilistic world, a la PSL, Lilac, etc., all these logics, with a way to break down the effects of the parallel in the distribution. And that comes from the outcome conjunction. So outcomes, and this connective is something that appeared originally in our work on outcome logic, where we were trying to unify correctness and incorrectness. So this was in a non-probabilistic setting. But we later instantiated to a probabilistic setting. And here is really, I think, the key insight about this connective as a logical connective, is that for many probability and for many analysis of probabilistic programs, you need to get your hands on the entire distribution. It is not enough to know what you do on one trace of your program. Especially if you're trying to build semantics of loops, you need to know what is the entire distribution your program is computing. And so in the probabilistic setting, this O plus basically enables us to reason about the entire distribution and break it down in compositional pieces. And for probabilistic concurrency, sort of the key insight was that these outcomes can be made effectful in the sense that they can be instantiated for different monadic effects, and they can be composed if you're careful enough. Okay? So this is sort of where this is coming from. But let me go back a little bit to the devil, to the semantics. And let's just look at, let me put these three things on. Let's look at the three components of the language, right? Of the language that we're trying to build and the semantics. So there's a component that comes from probability. And if you look at the work on probabilistic languages going back to the 80s, to the work of Kozan and others, there's the use of Markov kernels and convex spaces, convex algebras to give semantics to pure probabilistic programs. In concurrency, there's many ways of giving semantics to a concurrent program, but some classic ways would be using POM sets, event structures, and you're sort of trying to abstract away the scheduler through these algebraic structures. Now, in our case, we also want to have control flow structures. We want to have if-then else's, while loops, and we want those to, to be able to use tests that are Boolean, but also probabilistic. And we want to combine these three things. So when it comes to just programs with control flow, I mean, there's also structures, very old structures, using Boolean algebra and control flow graphs. And really what we were trying to do is mix these three together. Now, the mix of concurrency and control flow just on its own is already quite brittle in the sense that if you're not careful, your variables might be changed between, your Boolean variables might be changed by parallel threads, and your interpretation of if then else might break. But now we're trying to put all these three together, right? So this is sort of where we are. And we couldn't find anything in the literature that would enable us to capture semantics of this. So we came up with a new structure, which we call POM set with formulae. So POM set is the branching structure that captures the concurrency. The formulae are formulae that will capture the control flow. And then the nodes of the POM set are going to hide the probabilistic actions that will only be instantiated when you need them for the program logic. Okay? So this POM set with formulae are a new structure, and here's one example. For instance, if I have a program, an if-then-else, so here's a sort of nested if-then-else, this would be what the semantics would look like. And here A1, A2, A3 could be probabilistic programs. So the POM set will basically have two types of branching. So this is sort of the difference with the usual POM set semantics. Certain nodes, like for instance, Y1 and Y2, correspond to the branching of the first if. Okay, so the node X is at a point. So imagine in some program execution, I get to X, and I'm at the beginning of executing this if-then-else. So at that point, I branch, and I record in my formulae that I branched. And I branched using X. So the formula for Y1 is X, and the formula for Y2 is not X. And then when I do the second if-then-else, I accumulate the tests I've made so far. So what this formulae gives us is a source of how I got here. Okay, so basically, if at some point I unpack inside Z1 what probability distribution I have in there, I can tell you exactly what choices you made in your control flow program to get there. And this, as it turns out, is key to get a compositional semantics. Because if you don't have this source of control flow, then you might be interleaving threads you shouldn't be interleaving. And this is sort of where the idea comes for this. And so we have this POM set with formulae, and then at some point in our analysis, and I don't have time to show that, we are going to linearize this in the same sense, as linearization happens in concurrent separation logic. But in that linearization, the fact that each action is probabilistic is going to be taken into account. And so the probability distributions are going to be built compositionally as you do the linearization process. And so when you're done with your linearization process, you have a state transformer that tells you for every program state that you begin with, what is the probability distribution of output states that you end up with. And that sort of abstracts away the scheduler. Okay, okay. And so this is the language we gave semantics to, where the program actions are probabilistic, and the language semantics is a function from commands to this POM set with formulae. And there's, of course, for each program operation, we had to come up with suitable POM set operations that capture the right semantics. So for instance, for if then else, this POM set with formulae come equipped with this guard operation that basically annotates the formulas in the right place. And the fixed point, so the fact that the while loop is a list fixed point, this is where the work is in developing this new structure, because you basically need to show that this POM set with formula form a DCPO and that you can compute fixed points and so on. And that's where the technical sort of meat is. And so that is available in one of our archive drafts on this. Okay, I would like to spend the last, I know I'm running out of time, but I would like to spend the last few minutes just giving you a glimpse of the logic. So these are the probabilistic assertions. There's our sort of outcome conjunction that says I can sample from a distribution and do a conjunction of formulas. From these, and so the rules I'm about to show you do not include unbounded loops. So this is like without the loops for a second. For these type of assertions, we came up with rules for all the program commands, including a bounded loop, so a for. But let me just zoom in. This is, of course, I don't expect you to read this. Let me just zoom in on one of them. This is a simplified version of the sampling rule. And the sampling rule says, so this is a, sort of a simplified version that says, if I'm sampling from a distribution D, and I'm storing this in a valid pointer, meaning that this pointer exists, then I can conclude at the end that my variable is indeed follows this distribution D, okay? Now with this in mind, or with this sort of set of rules, we can go back to our example, and we can actually prove that our variable Z built with this XOR from a low randomness source and a high randomness source ends up being a good source of randomness. So the proof has two steps, basically. The first step is to show that if I keep my assignment x1 in the beginning, because I told you that if you swap it, then you run into trouble. But if you keep your assignment there, then what do I want to know about x1 that will be useful in my proof later? I want to know that x1 does not leak information, meaning that, at that point, x1 is there, but I cannot use the information from x2 to set anything, okay? So here is, so you can focus just on the last line that says, if my y, my variable y, so this is an invariant, if my variable y is Boolean, meaning, it was 0 when I set it, but I don't know if my scheduler has changed it, so my invariant has to basically consider both options that could be 0 or 1. Then the assignment of x1 becomes y. Also, the only thing I can say is that my x1 is either 0 or 1. Okay? So there's nothing here. Basically, I didn't learn anything new in some sense, but that's good news. So I can prove, using the rules I showed you before, you can ignore the proof, but I can prove that the assignment of x1 is y, only knows that y exists and is a Boolean variable. Okay? With this triple at hand, you can then use that triple and the sampling rule to go further and show that the value of z is indeed a fair coin. So how does this work? I basically, I start with the triple I want, and this is a very sort of classic program logic proof. I start with the triple I want, and then I apply the rules, the structural rules that the program structure tells me to. In particular, I have to apply the sequencing rule that will allow me to break the sampling from x2 and the sort of the building block for z being XOR. And so you end up proving that, so here on this side, you end up proving that if x2 is a Bernoulli sampling, then x2 is indeed, you can deduce that x2 is distributed as a Bernoulli variable. And that's a simple application of the sampling rule. And then on this side here, I didn't have space on the slide to put the rest of the proof. But on this side here, you use part of what we proved with this triple to basically then combine in the sequencing rule that the XOR takes the value from x1, which I know is either 0 or 1, and takes a value from x2, which is this Bernoulli distributed variable, and ends up building this new variable that is indeed a Bernoulli distribution. So I don't expect you to read this slide. I just wanted to sort of put on one slide the proof. Yes?
So, yeah, it's very nice. I was just curious, what would break? What will this proof break if you sort of flip the order of the two assignments?
So in this star here, which I haven't shown you, you wouldn't be able to basically use the x1 is in 0, 1. Yeah. Yeah, so that, yeah, you it just made me realize that should have been my next slide, which I didn't put. Yes. Okay, I'm coming to the end of my time. So I'll just conclude here and take questions. I hope I gave you a glimpse on why these probabilistic concurrent programs are an interesting class to look at. I mean, randomized distributed sort of algorithms and systems have been studied for a long time, but there's a lack of formalization in that world. And I think we, as the verification and semantics community, have a good playground there to actually contribute. With all these advances we've seen in program logics in the last 5-6 years on probabilistic and concurrent analysis, I think this is a great time to be looking at this. As I said, the work on Lilac and Bluebell and PSL and outcome logic, there's a flurry of really interesting things coming out at the moment for programs with probabilistic variables. So it's a really exciting time to actually try to tackle this class of programs. It's a good playground for us as formal methods people because these interactions between randomization and concurrency are really subtle. So it's very easy to make a mistake in a pen and paper proof, really easy. And so having formal models and program logics ensure correctness, compositionality is a big thing, and I think we'll see a lot of interesting work coming out. And so our work focus on sort of the denotational model, but I'm sure that there's other approaches using operational semantics and other things. But our work has basically focused on this idea that you can have a denotational model that enables you full reasoning over the distributions and how to derive a program logic from there. So this is work in progress. More is on the way, and a little bit of advertisement. This is the main work of my student, Noam Zilberstein, who will be coming up on the market next year. Go and see his talk at Popple this week. He's doing a lot of cool work, and I think this is nice work, and I hope you enjoyed the little glimpse I gave you from the work. Thank you. Ilya.
Thank you. It was a very nice talk. So I'm still thinking about the initial example that you've shown with the adversarial scheduler, that when you swap the two statements, check out the value and shows us the one that you don't want to. So it seems like your reasoning principles are geared towards this adversarial scheduler, but I would imagine in reality, most of the schedulers don't have this power, so they would give you like something close to like uniform distribution of picking one step of each thread, or maybe something like slightly biased, but like without access to the state. So would you be able to encode all this spectrum?
Yeah, so that's an excellent point. So indeed, we are at this extreme. So we are developing our work at the extreme of the adversarial scheduler. You are right that it would be really interesting to have a shade and that you could control how adversarial your scheduler might be. What we've done so far, you can't. But for instance, in this convex power set world of the work of Annabelle and others, they have looked at variants on the convex power set that represents different types of schedulers. So I would imagine, and I don't want to say that it's easy, but I would imagine that one could draw some inspiration from there and bring it here. But yes, that is definitely not something we've tried yet. But it's a very interesting point. Thanks, Ilya.
Thank you so much. I was just wondering with the POM sets, I may be misunderstanding it, but does that suffer from state space explosion in practical applications?
Yes, in the sense that, well, yes and no. So yes, if you do it naively, you're going to end up with a huge structure. No, in the sense that you can reason symbolically, so you don't need to build the whole POM set. And if you reason symbolically, then you can tackle the state space explosion. That's not something we have done so far, but that is something that has been done in concurrent work, and I would expect that transfers here as well. But yes, that is indeed like the downside of a lot of the denotational semantics for concurrency, is that you're trying to capture the whole behavior. And when you do that, there's no running away from the fact that you need to encode the whole structure. Yeah. Oh, sorry.
There are two things I have not really understood. One is you don't seem to have synchronization primitives. And second is, if the scheduler is follows a random law, and you have random choices in all processes, I don't understand how the output can be independent of the distribution used by the scheduler.
Okay, so that is indeed an assumption we made. So our scheduler is not randomized. Our scheduler is a regular sort of non-deterministic scheduler. And sorry, what was the first? You asked something else. Oh, synchronization primitives. We don't have synchronization primitives so far, right? So that's something we're actually thinking about right now, is how to add some form of synchronization. But so far, it's a really plain language that if you put a parallel in, you're sort of thinking in the back of your mind, you're going to do all interleavings.
All parallelism logic.
Yes, yes. So it is in that sense maybe I mean, it is a first step towards something, but I agree that might not be the most realistic step. It is enough, though, for the dynamic philosophers, it is enough. So for some things, it is enough. Yeah. Oded.
Thanks. I guess to follow up a little bit on Ilya's question, this adversarial scheduler that can see into the variables you've sampled so far, I don't know, maybe it feels a little weird for concurrency, but it feels like in many cryptographic protocols and kind of zero knowledge proofs, that's the kind of adversary that people are considering. I was wondering if you think that can be applied to analyzing these sort of protocols.
Yeah. So in the original PSL work, they already sort of exploited some of these cryptographic protocols. We haven't spent much time looking at versions where the parallel would make a difference. So all the examples we can do so far, they sort of were already covered by the PSL work or the follow-up work on conditional independence in any case. But yes, it is a good point that making this adversarial assumption is something that in the more security world might make more sense. And some of the randomized distributed algorithms we've been looking at, this assumption is made. So yeah, thanks.
So my question is about the way you write your specifications. So these are in sort of standard pre-post condition form.
Yeah.
So I was wondering if you extend to omega regular, temporal logic, infinite computations, would the same sort of theoretical foundations that you're putting down, would those still work, or are there special challenges that you?
So I didn't have time to show this, but in this work on unbounded loops, we actually have to take into account infinite traces because, as it turns out, for some of this probabilistic reasoning, finite traces are just a bad approximation, so the probabilities you get are just incorrect. And so there, we do talk about infinite traces, but not in the sense, so the logical connectives still don't talk about omega regular, but the traces we consider are infinite. Yeah.
So, but the specifications are still...
They are still like this, yes. It would be interesting to see if one could use omega regular languages, yeah, sure.
So one of you showed two examples. In one, you could prove a whole triple, but in the other, your proof failed. But I'm wondering if there is something by the way of a counterexample or a demonstration that could actually show the information leak.
Yes. Okay, so we haven't done that yet, but that is something that's very close to my heart. Sort of this counterexample generation, like what I envisage, but again, we haven't done it, is having some sort of bi-simulation construction proof that fails. And if you do it in a stepwise fashion, but then we would need also some form of operational semantics, you can actually trace back where it failed. And that is something I would really, really like to do, but we haven't done so far. But yes, you're right. Like the fact that our proof fails still doesn't tell us that some other proof method might not work. What we really need is actually a counterexample generation method. Yeah.
I have the impression that in this talk you make a bounded non-determinism hypothesis. Is
yes,
it true?
Correct.
Okay.
Correct. We make all kinds of bounded assumptions. Yes.
That's disappointing for me.
No, but Patrick, we have solved that part in the next paper, in the notational. So we're working.
The other talk.
You have to choose. We're working on it, one step at a time. Okay.
Okay, that's the time we have. Let's thank Professor Silva again.
Thank you.